Hi, so we're going to pick up where we left off when the Zoom crashed. So some of you already saw this on Discord, which is great. For those of you that were unable to see the Discord or join the Discord, this is what we finished up class, was going over the solutions of our breakout room work. These solutions are also posted on Canvas under the activities solution. I'm going to kind of walk you through the thinking here. So here we're given a graph of f of x, and our goal is to draw f prime. So the notes that they've given you over here kind of take you through the thinking process. So this is the order that I approach these graphs as well. The first step I would think about is where would the derivative be 0? My derivative is 0 whenever my function has a turning point. So when f has a turning point, or in other words, when f itself is a constant. Sometimes I have a graph that's constant for a long time, and then I know the derivative is 0 during that entire interval. Frequently we have graphs that do like this, where the graph turns around, so it's constant just at that teeny tiny point where it's turning around. Constant is horizontal, that's where I'd have a horizontal tangent line. I show that a value of a graph is 0 by when it crosses the x-axis. So what I've highlighted in pink should represent where my derivative graph is going to cross the x-axis. What's highlighted in yellow is when f is increasing, and that is when my derivative should be positive. What's highlighted in green is where my original function f is decreasing. That's where my derivative should be negative. So my graph is below the x-axis. If my actual function has a cusp, then the derivative is undefined. And so I can think ahead for my graph. Undefined, we'll kind of come over here and an aside, can basically look in three ways. I can have a pretty smooth graph that just has one hole missing, but the graph in general looks pretty. I can have a graph with a hole that starts and stops. My graph can go like that, stop, and jump up and start again in another place. So my hole can look like that. And I can also have asymptotes. So I'm not entirely sure what this graph will look like at that point, highlighted in blue, where there's the cusp. But the graph of the derivative will be undefined there. So I've got one of these three options. There's going to be some sort of start and stop. After I fill in the zeros, I'm looking where it's yellow, my graph of the derivative is positive, which means anywhere I've highlighted yellow, my derivative should be above the x-axis. And anywhere in green, my derivative is a negative value, so it should be below the x-axis. The derivative is the rate of change. So I can see here my graph starts out steep and gets flatter and flatter. So these are positive numbers that slowly get smaller and smaller and smaller until they hit 0. Now this green section of the graph has rates of change that are negative because the graph is decreasing. It starts out decreasing a little bit, it gets pretty steep, and then right around here, the graph starts to flatten out again. So maybe this is like negative a fourth, negative a half. Here the slope is negative 1. Now as it starts flattening out, we get again negative a half, negative a fourth, until the slope is again 0. So the numbers get more and more negative. Oops. And then they're going to turn around. They're still negative, but now they get closer and closer to 0 until it crosses 0 again. Now this yellow strip, my graph is increasing, so the derivative is going to be positive. It again starts out flat and then gets really big. So my derivative should start increasing here more slowly and then increase faster. And then exactly at the cusp, the derivative is not defined. Now it's going to be one of those scenarios that jumps. How do I know it jumps? Because right after the blue point, my graph is increasing, and then immediately it switches to decreasing. That means my derivative is getting more and more and more positive. Maybe this has a rate of change of positive 3. And then it jumps down to all of a sudden being negative. Now I have a rate right immediately on the other side of the blue mark. I have a derivative of maybe negative 3. And then it gets less and less negative. This graph is still decreasing, but it gets flatter. Here it looks almost totally flat, so my derivative should be close to 0. So we jump down here to a negative number, and then it stays negative because my graph is decreasing, but it gets closer and closer to 0 as the graph flattens out. So I'll kind of trace over this in red, hopefully. So what I'm tracing over in red would be a picture of the derivative, f prime of x. Then we went on, after you guys did that one, you were thinking about number 3. Number 3 is leading us into the new idea of what I've highlighted in yellow, what could be possibly a second derivative. So we're going to kind of go through the same exercise to draw the first derivative, and then once we have the first derivative, we can find its derivative, which would be the second derivative of my original graph. Again, we're looking at the actual graph of f of x, and we want to draw the derivative. So following the notes from number 2, we're going to pretty much do the same thing, but we'll try and do it a little bit quicker now and do it exactly on the graph. So the first thing we look at is when the derivative is 0. The derivative is 0 when my actual graph has a constant rate of change, has a horizontal tangent, which is what I've highlighted in pink, where the graph turns around. So where I've highlighted it in pink is where the graph of my derivative should cross the x-axis, because the derivative should have a value of 0. Now where my graph is increasing, it goes up from left to right, my derivative should be positive. So that means it's going to be above the x-axis. So starting here, it's very steep, so it has a big positive number, and then it gets flatter as I approach that pink point. So I'm going to start out at a big positive number, and my derivative, the rate of change, is getting smaller and smaller and smaller until right here the rate of change is exactly 0 when I have that horizontal tangent. Over here we have something else interesting, because it seems to be increasing faster and faster and faster, but now there's a sharp point. And then it kind of slows down, right? It's increasing pretty fast, and then immediately the slope of that graph changes to be flatter, right? This piece, I'll kind of highlight over it in blue, is flatter than the previous piece. It now looks green because I did blue on top of yellow. So the green piece is still increasing, so the derivative will still be positive, but it's going to immediately jump. So maybe right here on the left of the blue, maybe that's a rate of change of 3 to 1, and then it immediately jumps over here to being 1, right? So there's going to be a break. I'm going to have something that's going up, 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 and then it's going to break, and it's still going to be positive, and then it's going to stay the same. Because that piece that's highlighted in the blue-green, the blue on top of the yellow, that is a linear function, and a linear function has a constant rate of change, so a constant derivative. So following the path here it's yellow. When I start at my first yellow, this graph is going to have a positive derivative because the graph is increasing, and my derivative is going to be getting bigger and bigger and bigger and bigger and bigger, and then right here, all of a sudden it's going to stop. There's no derivative at the sharp point. It's undefined, and it's going to pick up again. It will still be positive, but it's going to be a smaller positive number, and then it will be a horizontal line because it will stay constant, because the green piece has always the same slope. So now filling in the negative parts, so in between these two pink lines where the graph turned around, my original graph is decreasing. So wherever my graph is decreasing, my derivative should be negative. Just like in the first example we did, it starts out getting steeper and steeper and steeper, so the numbers get more and more and more negative, and then somewhere around here, the graph starts to flatten out again. Still decreasing, so I have negative numbers, but that are getting to be bigger negative numbers, so getting closer to 0. So it looks like this. It's getting more and more and more negative, and then the derivative is going to turn around. I still have negative numbers, but they're getting closer and closer to 0 again. So again, what we've drawn in red here would be the first derivative. Now we're trying to do a second derivative. The second derivative is the derivative of the first derivative. So I'm going to do exactly the same process that we just did, but I'm now going to apply it to the red graph. So if I'm looking at the red graph, we'll use the same notation. Where it turns around, its derivative will be 0. So it's going to have a 0 right about there. Right? I'm going to use the blue for my second derivative, the derivative of the first derivative. Where my red graph is increasing, my first derivative, its derivative, the second derivative, should be positive. So here it's going to be above the x-axis. It looks like it's getting faster and faster and faster and faster, and if my function is undefined, its derivative is undefined. And then where this graph is decreasing, its derivative should be negative. So it looks like it's starting out pretty steep, so very negative numbers, and then it's getting flatter. So the numbers are getting to be less negative, approaching 0. So I might start out somewhere down here, and then eventually they'll cross 0 right there. Now the interesting part is this flat piece. So this flat piece, of my graph, a horizontal line has a derivative of 0. So now at my graph, my second derivative jumps down here, and for that entire horizontal stretch, the derivative stays at 0. So what I've drawn here in blue would be the second derivative. What I want to look at now is how does the second derivative compare to the original graph. So I'm going to see if I can possibly erase my first derivative without erasing my second derivative. Yay. And let's see if we can think about how is the second derivative related to the actual graph. So we already know a few things. We know that if I take my original function f, and let's look at the f prime and f double prime. If f is increasing, the first derivative is positive. If f is decreasing, the first derivative is negative. If my function is constant, the first derivative is 0. I also know that if my first derivative is increasing, the second derivative should be positive, right? Because it's the derivative of the derivative. If the first derivative is decreasing, my second derivative is negative. What does it mean to my actual function if the first derivative is increasing? So if the first derivative is increasing, we said the second derivative is positive. So let's kind of highlight that in blue. Let's erase all of these other colors here so we don't get confused. So the first derivative was increasing. That's when I drew this piece in blue. My second derivative is positive. So let's look at the actual original graph. This is what the graph looks like when the second derivative is positive. So what the graph looks like there, that curving up, that's the rate of change getting faster and faster and faster, right? It was negative numbers, and they're getting, here the negative numbers are getting less and less negative, so that's bigger numbers. And now they're turning to positive, and it's getting steeper and steeper and steeper. So the slope keeps getting bigger and bigger and bigger. That makes this concave up. So if the second derivative is positive, my original function is concave up. That's what that means. Similarly, if I look here, we know, because of what derivatives mean, that if the first derivative was decreasing, its derivative, the second derivative, we would draw as negative. So that's this piece. Let's look at what that tells me about my original function. So if my second derivative was negative, now my original function is concave down. So that's what the second derivative tells us about the original function. If the second derivative is 0, then there's no concavity, right? A line is not concave up or concave down. So when the second derivative was 0, then there's no concavity at all. So, oops. If the second derivative was 0, where there's no change in our first derivative, then there's no concavity in the original function. And then here I've also included, and this is in our Canvas as well, here's a much nicer picture of the first and second derivative that was in the solutions. So that was what we were able to finish on the Discord. If you want further notes and lecture on the second derivative, then look at the next video as well.